here is a sample problem that's related to the work done on a spring and its relationship to the energy transferred to the spring. A massless spring located on a smooth horizontal surface is compressed by a force of 63.5 Newton, which results in a displacement of 4.35 centimeters from the initial equilibrium position, as shown in figure 5.16. So this is figure 5.16. A steel ball of mass 0.75 kilogram is then placed in front of the spring, and the spring is released. So this here in part A, we have the spring in its equilibrium position, and then in part C, the spring is now compressed, and now we have a steel ball that is placed in front of a compressed spring. So the problem is, what is the speed of the steel ball when it is shot off by a spring, that is after it loses contact with the spring? So we would want to know this velocity here. Assume there's no friction between the surface and the steel ball, and the steel ball will simply slide across the surface and will not roll. So we do not worry about any friction. So, and we need to solve for the speed of the ball when it is shot off by the spring. So this velocity Vx. All right, so first let us identify the given in our problem. So first we're given the force, which is equal to 63.5 newtons. This is the force that is being exerted on the spring to compress it, and which results in a displacement of 4.35 centimeters. So this is our x. That's equal to 4.35 centimeters. And we need to convert this into meter by dividing this by 100. So that's going to be 4.35 divided by 100 is equal to 0.0435 meters. So again, we divide it by 100 to make it meters. And then we have the mass of the steel ball. So the mass of the steel ball, let me just call it M ball, is equal to 0.075 kilogram. And we are asked to solve for the speed of the ball. So we have V, in this case Vx, because that's actually what's being written in our problem. So we'll keep it that way. Vx is equal to question mark. That's what we need to solve for. All right, what are the things that we know? So we know that F is equal to Kx, or the force exerted on a spring would just be equal to the spring constant multiplied by the compression or extension. And we also have work is equal to the work done in compressing the spring, or the work done on the spring, is equal to 1/2 kx squared, which is just equal to the energy that is being transferred into the spring. So the work done on the spring is equal to the energy transferred to the spring. And also this energy here could become the potential energy of the spring. And since when the spring would now expand, or would now decompress rather, as in part C, this potential energy becomes kinetic energy. So it will be converted into kinetic energy, which will be given into this ball right here. So let me just repeat that. As work is being done on the spring by compressing it, this work becomes the potential energy of the spring. But the moment that we remove the force that compresses the spring would now decompress. It would expand to its original position, and therefore it would actually give its potential energy to the ball, allowing it to move forward. And this potential energy is converted into kinetic energy. And we know that kinetic energy, Ke, is going to be equal to 1/2 mv squared. All right. So the first thing that we need to do is to solve for K, so that we would use this K now to substitute in our second equation to solve for work, because this work right here becomes our potential energy. And once we have our potential energy, that potential energy becomes kinetic energy, which would later on allow us to solve for the final velocity. So let's do this step by step. The first step is solving for spring constant. Solving for K, or the spring constant. So we have our formula, F is equal to Kx. So we have our F, which is 63.5 Newton, is equal to K, which is what we need to solve for, multiplied by the compression, and in this case 0.0435 meters. So our K is equal to, so 63.5 divided by 0.04. So plugging this in your calculator, this would actually give us that the K is equal to 1459.8 Newton per meter. This is our spring constant. Okay, so we would use this K now, or the spring constant, to solve for the energy that is being transferred into the ball. So say solving for the energy transferred to the ball. So once again, the work done on the ball is just equal to the energy transferred to the ball, which is 1/2 kx squared. Let us substitute the values. 1/2, our K is 1459.8, multiplied by the compression, which is 0.0435. Do not forget to square it. So the energy transferred to the ball is equal to 1.38 joule. So now, once again, this energy is actually potential energy that is being stored in the spring because of the work done on it. Now, once the spring decompresses, this potential energy is translated to kinetic energy. So this potential energy becomes the kinetic energy of the ball. So now we could use this kinetic energy to solve for the velocity of the ball. So now we have solving for the velocity of the ball, or Vx. So we use the formula Ke is equal to 1/2 mv squared. So let's substitute our values. Our Ke is 1.38 joule, is equal to 1/2 multiplied by the mass of the ball, which is given to be 0.075 kilograms, V squared. So manipulating this equation, we should be able to get 6.06 meters per second. So I encourage you to maximize your calculator in solving this. So you may use the that function of your calculator that allows you to solve for the unknown. And this is our final answer.